Chapter 9, G transform. We have studied Fourier transform and it is very powerful tool, but it has a limitation. Some functions do not have their Fourier transform. For example, exponential t is t1 looks like this, increasing function. When we take integral, it will be blow up, so there is no convergence. Then, how do we do frequency analysis for such signals? We need more general and more powerful tools. In circuit theory 2 and signals and systems, we already studied Laplace transform for continuous time signals. Here, we will study the G transform for discrete time signals, which is a counterpart of Laplace transform. So, we have studied n domain, the time domain, and frequency domain, so-called omega hat domain, like this. On top of that, we will study Z domain. Some problems easily solved using frequency domain and Z domain, but the implementation domain is time domain. So we will study all together. The definition of G transform of discrete time signal is summation xn gn minus n from minus infinite to infinite with respect to n. And there are two sides, so we call it a bilateral G transform. When sequence starts only n0, it is called unilateral. Without state otherwise, so we will consider bilateral G transform as a G transform. The time domain and the G domain here, the simplest one, xn with delta n, then xg will be n is from 0 to minus infinite to infinite, delta n z minus n. When n is 0, it will be 1. The others will be 0. So delta 0 z minus 0 will be 1. What about shifted by 1? Then xz will be n is from minus infinite to infinite, delta n minus 1 z minus n. When n is 1, then delta is 0, n minus 1 will be z minus 1. What about shifted by n0? So z will be n is minus infinity to infinity, delta n minus n0, z minus n. So when n is n0, delta 0, z minus n0. So z minus n0. If is a weighted sum of delta n, xg can be expressed, n is from minus infinity infinity to infinity. From definition, k is 0 to m x k delta n minus k z minus k. Here's k is 0 to m x k n is 0 minus infinity to infinity delta n minus k z minus k. This is m minus k. So it is k is 0 to m x k z minus k. The signal x n is 2 delta n plus 4 delta n minus 1 plus 6 delta n minus 2 plus 4 delta n minus 3 plus 2 delta n minus 4. So when you take G transform, it will be 2 and delta n will be 1, and each term take G transform and summation, because G transform is also linear, which we will study later. Okay, so here 2 to plus 4 g minus 1 plus 6 g minus 2 plus 4 g minus 3 plus 2 g minus 4. So in the finite sequence, we can express a polynomial of z. If polynomial z is defined in like here, then we can have n domain, time domain signal using inverse G transform, expressed with delta function like that. Here we can have questions. Does xz always exist? Regarding existence problem of G transform, if xz G transform exists, then is there one-to-one mapping for G transform? That means there is a unique solution regarding the uniqueness of G transform. Let me show an example here. Xg of left signal actually is 0 will be 1, it's 1 will be 2, so 2 will be 4, something like this. Here, when 0 will be 0, will be n is 0, so 2n will be 1, so minus 1. When it is minus 1, it will be minus half. It's minus 2, it will be minus 2 minus 2 quarter, something like this. So from definition, and is from minus infinity to infinity to n un g minus n, and starting 0 to infinite to n g minus n, and is from 0 to infinite to g minus 1. If geometric series is converged, means that it will be 1. So when the absolute value of z is greater than 2, it will be minus 1 to z minus 1 will be 1. What about this? xz, the second one, and is minus infinite to infinite to n u minus 1 n z minus n u n. And this u minus n u minus n minus plus 1 will be 0, starting minus 1 to here. So it is minus 1 and minus infinite. It's minus 2n z minus n, and is minus infinite to minus 1 will be minus n z minus n. So it will be and is minus infinite to minus 1 to have z minus. For simplicity, let's change k. K is 1 to infinite k. Actually, it is k from 0 to infinite z k plus 1. To converse of this term to half z should be less than 1. So z should be less than 2. So it will be minus 1 or half z 1 plus 1. So when you change this, it will be 1 minus or half z minus or half z. So it is 1 minus 2 z minus 1 is 1. Okay. Let's compare this. Transform is the same, but region of convergence are different. So to define a G transform, you can define the G transform uniquely with G transform and ROC together, region of convergence. So when you talk about the G transform, you should talk with ROC together. So xg exists only when xn, gn is converged to something before less than infinite. The set values of z in the complex plane is called region of convergence of the G transform. the difference ROC implies different G transform, even though the expression of G transform may be the same. Okay. Here we call zeros means, so make G transform 0. We call it 0 when the Z makes infinite will be poles. Here is an example. So when you express this, Z square over G square plus 1. So we can express as G square G plus G J times Z minus J. So when Z is 0, so twice will be 0 of Z. So numerator, the roots of the numerator will be 0. What about J or minus J? Then, since denominator becomes 0, so the absolute value of hg will be infinite. So we call poles of hg, and we mark x on the complex plane. Here's another example. hg is here, and when we decompose the terms, then like this. So zeros means a root of numerator here, and the poles is root of denominator. G is 4 plus minus J 3 here, so marked with X. So we can express an example 3 poles like that.